Welcome back, everybody. Okay. Second, I got one joining here. All right. Well, let us finish up this chapter 6, and then if there's any questions concerning chapter 6, we got a few slides, not very many more. Be done with that. If there's not any questions, I will then proceed with chapter 7. Okay. All right. So we ended up on slide 22, but I'm going to back it up a little bit. What we're looking at here now, there's two properties here that we need to distinguish. Okay, the first one is called ionization energy. Now, with respect to ionization energy, what this is a measure of the amount of energy necessary to remove one electron from an atom, from an element. Okay, so it's a neutral element. It has nothing to do with it being bonded to anything. It's simply a neutral element. And here I've highlighted sodium, for example. Okay. And this is how we write a reaction or a chemical or a process. We write an arrow, and to the left of the arrow are what we consider the reactants. And then to the left of the arrow, excuse me. And to the right of the arrow, I'm going to put in a different color, are what are the products, the result of whatever process we did. Now, in this particular process, we are taking sodium element, the atom, and we are measuring the amount of energy it takes to remove one electron, okay? That is called the ionization energy, the amount of energy necessary to remove an electron from a neutral atom. Now, I hope you can pick up on something here and what we've been talking about is that all metals lose electrons, okay? And all nonmetals gain electrons. So if you give it some thought, you can just do a relative quick comparison between a metal and a nonmetal because metals want to hold on. Because metals want to lose electrons. Okay, because metals want to lose electrons. When we want to compare the relative energy to a nonmetal, we can already start to deduce that for a metal, the amount of energy to remove an electron would be much less. Okay, give that some thought here than a nonmetal, because the nonmetals want to keep their electrons, they want to gain electrons. The other thing too, if we look at a periodic table, and what we're doing is trying to predict this ionization energy. We talked already about the relative radius of the atoms as we go down the periodic table. Now, if we, for example, were to compare, see, we know that because everybody in group 1 has one valence electron, okay? Now, if we compare within that group, okay, just within that group, the amount of energy necessary to remove an electron, we can see a little trend here. We can see that, for example, lithium and cesium, number 55, share one property, and that is one valence electron. That is why they're in group 1, okay? The difference is this. For cesium, number 55, that one valence electron is in energy level number 6. So compared to lithium, where its valence electron is in energy level number 2, much further in and closer to the nucleus. So the amount of force necessary to hold on to that single electron, that attraction between the electron and the nucleus, for cesium stands to reason it is much less, simply because it's further away than lithium. whereas that single electron for lithium is much closer. So the fact that cesium is bigger and than lithium, and that they both have 1 valence electrons, the fact that cesium is bigger, one can conclude that the amount of energy to remove that 1 electron for cesium will be much less than the energy for lithium. Okay, simply because it's that 1 valence electron is further apart. And that will be true for everything down within the column. So with that in mind, it says it's easier to remove electrons from a larger atom simply because they're further away. The electrons are further away from the nucleus, and that force of attraction is much less. Okay, much less. So the trend is this: as we go from up a group, or as we go up a group, the ionization energy increases. All right, or it decreases as we go down the group, whichever, tomato, whichever way you want to look at it. Now, with respect to going across the group, okay, we talked about this briefly when we looked at the radius as across the group. We said that as we go across the group, and then we pull up the periodic table again, and we will compare, let's say, let's do a quick one. We compare sodium with chlorine, okay? We're comparing the atoms. We said that chlorine would be smaller because one reason is that chlorine has a lot more protons and electrons than sodium. Therefore, the nuclear force is much greater. There's more force between the positive protons and the electrons. The result is the electrons get pulled in because there's more force of between the positive and negative. While the same is true with respect to trying to remove an electron, because they're being pulled in tighter than, say, the ones to the left in the same period, it's going to take more energy to remove an electron as you go across the periodic table. Okay, for the same reason, the radius is much smaller as we go across the periodic table. And what we can do is we measure the ionization, the energy, and we can plot a graph. Now, what we have on the y-axis, which is this axis here, is energy. Okay, and the units here is electrovolts, but that's just energy units. We'll call them energy units. And in the x-axis is simply the atomic number of the element. So if we begin with element number 1, which is obviously hydrogen, and we measure its amount of energy to remove an electron, it's somewhere, if we look at the number in that scale, maybe about 13.5-ish units of energy. Okay. Now, as we go across the periodic table, we hit helium. It's one of the noble gases. Wow, the amount of energy now for helium to remove an electron, the ionization energy, jumps up from 13, roughly double, all the way almost to 25 units. Okay, 25 units, because again, more protons, more electrons, more energy to hold on to those electrons. They're not going to give them up that easily. Then as we go across the periodic table, we flip around to lithium, it drops again. Here's lithium right there. Element number 3. Approximately 5 units of energy to remove that electron. Much less, okay? Simply, again, because it's a metal. Now, as we go across the periodic table, you can see that we go all the way across to neon, and in neon, that energy increases. So as you go from atom, yes, there's some little hopping here and there, but the general trend is as you go across the periodic table, the amount of energy necessary, the ionization energy is greater. So we hit neon. You can see neon is roughly about what, 21 and a half units of energy compared to 5 units of energy for lithium. So we go over across the periodic table, go around again. After neon, we got sodium. And the same general trend, okay? But the slope of that energy kind of, as you go across the periodic table, the arrow kind of straightens up a little bit. And that makes sense because as we go across the periodic table, we're getting bigger and bigger elements, okay? Bigger and bigger elements. And so larger in size, those electrons that we want to pull off are getting further and further and further away from the nucleus. So the general trend as we go down the periodic table, the ionization energy decreases even within the same period. It basically almost flattens out. Okay. All right. So that's the general trend of the ionization energy. And this is the amount of energy necessary to remove an electron from a neutral atom. Okay. From a neutral atom. Now, a couple of questions here. They're asking you, which has the higher IE and why? All right, so we got three series here, three elements, chlorine, aluminum, and magnesium. Well, to answer that question, we got to find them in the periodic table. When we do that, we see that they're all in the same group, specifically not group, but same period, and that is period number 3, okay? So we're going across the periodic table. And so what we find here, just like the radius, chlorine radius is greater for the radius for chlorine is much smaller than it is for magnesium. The same trend will be found with ionization energy. Furthermore, you even if you didn't know that, okay, you can see that of these three elements, 2 of them are metals, okay, and 1 of them, chlorine, is a nonmetal. Just with that fact itself, chlorine would have the greater ionization energy, okay, because it's a nonmetal, and it simply want to say holds on to those electrons much tighter. So it would take a lot of energy to remove one. Now, if you look at the next group, okay, we can see they're within the same group. And being in the same group, what they have in common is the same number of valence electrons. Specifically, they have 1 valence electron. All of them do. The difference is RB is much larger. It is in group 5 compared to the others. And B, not group 5, period 5, okay? Meaning that 1 valence electron is further away from the nucleus. So that means that it would take less energy to remove that. And lithium is in group 2, in period 2. So its valence electron is much closer to the nucleus. So it's being held on much tighter, okay, and then RB. And so RB being smaller holds on to electrons much tighter than the larger atoms. Okay, so there are YouTube on the course website concerning ionization energy. Of course, feel free to go up there and listen to them. Dr. Kim did a very good job explaining this, has some other examples for you to help you understand. Okay, now we talked about ionization energy, and we said again that is the amount of energy it takes to remove an electron from a neutral atom. Okay, not to be confused with this property, En, electronegativity. And that is the ability of an atom. This is very important. This is going to be very crucial with respect to bonding, the types of bonds down the road. So electronegativity is the ability of an atom to attract bonded electrons, okay? Bonded electrons. Now, fluorine is the most electronegative element in the periodic table, okay? And so it being the most electronegative, we're going to put it right there, and that's fluorine. And that's going to be our benchmark because that would assist us to determine and compare the electronegativity of other elements. because the trend goes from left to right. As we go to fluorine, electronegativity increases. And from the bottom of the periodic table toward fluorine again, the electronegativity increases. So we can, let's go back to the periodic table and do a comparison. For example, if we were to compare here's fluorine, so that's our benchmark, okay? And so if we wanted to compare the electronegativity of carbon with nitrogen, and let's say carbon and nitrogen are bonded together, they will make a bond together. The question is, which of the two, carbon or nitrogen, is the most electronegative? And that would be nitrogen, simply because it's closer to fluorine than carbon, okay? And the same would be true if we were to make a bond with nitrogen and oxygen. The electronegativity would be greater for oxygen. What does that mean? Well, we're going to learn that if nitrogen and oxygen are bonded together, oxygen, let me erase this one here real quick. If we were to make a bond between oxygen and nitrogen and oxygen, and I got nitrogen there, and I got a hyphen, a line that represents a bond between nitrogen and oxygen. The fact that oxygen is greater in electronegativity means that oxygen is going to pull those electrons, and those electrons are represented by that hyphen. That hyphen represents a bond. What a bond is two electrons being shared between the nitrogen and the oxygen. Okay, but we have unequal sharing. Why? Because the oxygen has a higher electronegativity than nitrogen. And so it's like a tug of war between, say, a 200-pounder and a 400-pounder. That tug of war and that rope represents a bond between the 200-pounder and the 400-pounder. And that rope represents those electrons. Well, obviously, the 400-pounder is going to pull harder than the 200-pounder just by virtue of its weight. And so the result is that in this case, the oxygen represents the 400-pounder and the nitrogen represents the 200-pounder. And so that bond between them, those electrons are going to be pulled toward the oxygen much greater. They're going to be around the oxygen much more than the nitrogen. That creates what we call a dipole, okay? Dipole meaning two poles. You're familiar with dipoles. Your battery is a dipole. Your car battery is a dipole. You got a positive and a negative. A magnet is a dipole. You got a north side and a south side. The earth is a dipole. We got a north pole and a south pole, okay? That's all it is, nothing real fancy. But that dipole that's created, which we're going to learn more about, gives the properties of solubility. Things like makes it more soluble in certain solvents, viscosity, some other physical properties, boiling point. We're going to learn all about that with time. We're going to be able to, just based on the difference of electronegativity of that bond, it's going to give us a ton of information. Okay. So electronegativity, don't confuse it with ionization energy. Ionization energy has nothing to do with any bonds at all. It just simply means is just a measure of number of electrons and the amount of energy necessary to remove an electron. Electronegativity is going to be very important when we start talking about chemical bonds. And that is a measure of an atom, of a measure of the attraction or the pulling of electrons onto itself in a bonded situation. Okay. All right. So obviously noble gases don't have any electronegativity because they don't form bonds. The octet is full. You know, that's it. They're done, so to speak, with chemical bonds. Electronegativity only deals with bonds. We're going to learn when it comes to bonds You would think with all these chemical compounds that are out there, there'd be all kinds of chemical bonds. But in reality, there's only two types of chemical bonds, okay? And that's what the next chapter is about, being able to deal with the chemical bonds and how do we distinguish them, okay? That being said, ladies and gentlemen, guess what? You are done with chapter 6. We're a little bit over 1/3 of the chapters, okay? 6 down. Um, Well, we got 14 to go. Was that 14? No. 14 to go. Does that make sense? No. How many chapters we got left, guys? Anybody know how many chapters we have? Nobody knows how many chapters we have? We got 150. How's that?
15.
15. Thank you. Yes, we got 15 chapters. All right. So any questions about 4, 5, and 6? Again, yes, Tuesday is coming up. We got exam number 2. I will be here, obviously. Okay. And if there, I'll be more than happy to answer any questions for 4, 5, and 6. Then we can answer them now if you like, because the exam will open from noon and end at 10. And so, if you don't have any questions, I'm going to continue with chapter 7. All right, let's go now. Chapter 7. All right, now this deals with chemical bonding. All right, there are 2 types of chemical bonds in that we're going to study. 2 types of all the chemicals that are out there. There's 2 types. All right, and we're going to use it. We're going to determine that, and there's type number 1. Type number 1 is a bond between a metal and a non-metal. You're familiar with one example right now: table salt, sodium chloride. Okay. The other type of bond is between a 2 non-metals. You're also familiar with that type. H2O is in hydrogen and oxygen. Each one are non-metals, okay, but they form a bond. And that is a very special kind of bond that we're going to learn about. So that table, that slide we had where we had metals and non-metals, metalloids, be familiar with that, because you need to determine pretty quickly who's a metal and who's a non-metal, because then you can determine what type of bond you're dealing with. Okay, of those 2 types. We were not going to have any metalloid interactions in this particular course, but if we were dealing with higher chemistry classes, yes, we would. But for us, we're going to be dealing simply only with metals and non-metals. All right. Now, there's, of course, there's a shapes table. And let me pull that up. If you've not done that, download it, make sure you download it. Okay. We're going to use it. We're going to use it quite a bit in this particular chapter, because this basically tells us the shape of the compounds that we're going to be working with. We're going to actually put them together, and we're going to notice this column here. There are 4 columns. Now, the first column is the general formula. I've highlighted that in blue. Okay. Now, the general formula, we're going to take the valence electrons of a combination of elements that we're going to work with, add them all up, okay? And from that information, we're going to determine how many bonds they have and so forth. And then we're going to come up with a general formula. Now, that general formula is listed as ABE. I repeat, it's a general formula. Many compounds will have this general formula. But based on the number of valence electrons they have and how many atoms you're working with, we're gonna get all that information together and come up with a general formula. Okay, A represents the central atom. So you're going to be told, always be told what the central atom is. Okay, and so A equals the central atom. B represents elements bonded to central atom. Okay. And E is what we call lone pair of electrons. Okay. Now, we have two types of electrons. First of all, every pair that we're going to be working with, every pair has two electrons. Every pair, again, has two electrons, and those are designated by a line. For example, if you look at this line right here, okay, where we got two spheres bonded, that one's an example. We got another one right here. Okay, that line represents two electrons that are bonded between those two atoms. Okay, and we're going to have two types of electrons. We're going to have the type that is called bonded, like that, those two arrows, and then not long. Let me correct that. I typed in LONGE. Lone is the word. Then we're going to have a pair that are not bonded. They're designated by two dots. And I'm pointing to those in the arrow. That is, those are electrons that, let me correct it, what we call lone pair. They're not bonded. Okay, so we have bonded pair and we have lone pair. And we're going to use the octet rule, because if you think about this, let's do a quick count. We got two electrons sitting right there. Down at the bottom, I pointed my arrow to. Let me try a different color here so we can make sure we're all talking about the same thing. I'm going to go to yellow. Let's go. So we got that lone pair and that lone pair. We got a total of 4 electrons, right? Okay. Now, this is a bonded pair denoted by a line. And the other is a bonded pair denoted also by the line. In that line represents 2 electrons. So if we count the number of electrons around the central atom, guess what we have? We have a total of 8. 4 electrons in 2 pairs that are bonded and being shared with another atom, and then 4 lone pairs that are not being shared with another atom. But there's 8 electrons around that central atom, the octet. Okay, the octet. With that information, we're going to come up with shapes and formulas and shapes to these compounds that we're going to put together. Okay, so we have general formula ABE. A is the central atom. B represents whatever is bonded to the central atom, and E represents, only for the central atom, lone pairs of electrons. There's lone pairs on other atoms that are not the central atom that we don't care about. We only care about the central atom. Now, once we know that, we have a general formula. And let me clear this up a little bit. Let me move this over here. Okay, and right here, clean up this a little bit. So once we have the central atom, we have 3 pieces of further information. If our central atom, the central formula, it ends up with an AB subscript 2, okay, then the next column tells you what is the molecular geometry of that compound. In this case, there's a shape there. A, we got a central atom, and then we have 2 atoms bonded to the central atom, and there's a 180-degree bond angle between the B's, the 2 items that are bonded to the central atom. And that has a shape named we call that linear. And there's the bond angle, okay? Then we have an AB3, which again, we have a central atom with 3 elements bonded to the central atom A, whatever A may be, okay? And that's it. And we have that particular molecular geometry, which we call trigonal planar. And the bond angle between in that particular geometry is 120 degrees. Now, the most common geometry we find out in chemistry is this AB4. Very common and found in a lot of different compounds. And that is what we have, the central atom, and there are 4 elements bonded to the central atom. And if we notice something here, remember that each line represents 2 electrons. Well, there's 2 there, there's 2 there, and so on down the road, 2 there. And so what happens, remember, the electrons have negative charge, and they want to separate, repel from each other as much as possible. And so when I got 4 bonds around a central atom, those electrons are going to want to split far away from each other. They want to pull away, repel from each other as much as possible, given their geometry. And that is what happens. You end up with what we call a tetrahedral, and where the bonds here are spread out as the best they can, given the size that they have and so forth. So we have what's called a tetrahedral shape, and that bond angle is 109.5 degrees. That is the most common type of geometry, the compounds that are out there. Now, we also introduced AB2, AB2E. E, again, represents the lone pair electrons in the central atom only, okay? So in this case here, we got 2 elements bonded to the central atom, and then we got a lone pair sitting up there. That lone pair are 2 electrons that are not bonded, they're just sitting there, take up a lot of space. The result is they tend to decrease that angle. So because these electrons, lone pair, 2 of them take up a lot of space, they push the other 2 bonded pair into each other. So that bond angle is much less than what we would expect to be 120, like up here, okay? But because of the lone pair taking over space, they push that bond angle, and we get a new geometry, and we call that bent. Now, if we add three bonded bonds to the central atom and a lone pair, which is many examples like this, ammonia is one example. NH3, we'll get to that. It has its geometry, its shape is the trigonal pyramid. And again, that bond angle, you would expect it to be 109, like the tetrahedral, but it's not. And it's not 109 because that lone pair, as the case with the previous example, takes up space. So they pull the bonds in. So that bond angle becomes less than 109.5. And then you have another example with 2 lone pairs on the central atom. Classic example of that is our good old-fashioned water, H2O, 2 lone pairs on a central atom. And those 4 electrons that are not bonded to anything, they're lone pairs, take up quite a bit of space. And so that bond angle really gets shrunk, much less than 109.5 degrees. Okay, so using this table, we're going to be able to come up with a geometry for the compounds, okay? And once we figure out the general formula, but before we figure out the general formula, you're going to be given elements to put together. We're going to use the valence electrons of every atom to determine the bonds, okay? And that's where, if you don't quite grasp where to get the valence electrons, refresh your memory in the previous chapter. but we're dealing only with the A metals, okay? The 1A through 8A, because again, that gives us the number of valence electrons. All right, so download that shapes table and get familiar with it. Okay, now the driving force, as I mentioned, was obtaining the octet, getting 80 electrons around. Now, with the exception is helium, which has 2, okay, and hydrogen. Hydrogen does not want 8 electrons around it. It just can't handle it. Hydrogen's rule is a duet, just like helium. Okay, so you'll always find hydrogen bonded. We're going to use quite a bit of hydrogen, but there's only going to be one bond to it, one bond, because its rule is a duet, not the octet. Everybody else has an octet rule. Okay, so the ultimate goal is to get 8 valence electrons, except for hydrogen and helium, obviously. Remember, metals lose electrons and become cations, and nonmetals gain electrons, become anions. Okay. Now, the first type of compound is the first type of bond is called an ionic bond. Okay. And that is due to the combination of a combination of a metal and a non-metal combination. Okay. So when you have a metal combined with a non-metal, you have what is called an ionic bond. Okay. A good example would be sodium chloride, good old-fashioned table salt, sodium chloride. Sodium is a metal. Chloride is a non-metal. Now, it could be any other lithium chloride, potassium chloride, any other metal, iron chloride, any metal. That is an ionic bond. Okay. Now, they come together because of the positive charge and the negative charge. Now, remember, we kind of touched on it a little bit. When I put these together, it's going to be the positive ion. It's going to be a combination of an anion and a cation. It's not a combination of 2 cations. It's not a combination of 2 anions. It's a cation and an anion. And I put them together such that I have sufficient negative charges to cancel out the positive charges. So here they're asking who's a good partner for the calcium ion. Okay. Well, it can't be the lithium ion because it's a cation. The only good partner will be the anion bromide. Okay. Bromide. Some examples, as I mentioned one sodium chloride, but we got calcium chloride. We also got calcium bromide, calcium chloride, calcium iodide. It's just any combination of a metal and a metal. There are literally thousands and not millions of combinations of ionic bonds. Millions, actually. Now, with the other type of bond, and I'm going to give it a different number. When you have a combination of 2 nonmetals, okay, 2 nonmetals, we have what is called a covalent bond. You also will hear the term molecular bond, okay? A covalent bond. Because what they do is they share those electrons in that bond. We will learn that the ionic bonds do not share. Ionic bonds, remember, the ions are coming together. We got a combination of ions. It is like 2 magnets coming together. And so we have 1 magnet, 2 magnets, and they attract to each other and they just attach each other. There's no sharing of that those electrons that they have. They come together by what we call an electrostatic attraction, just like two magnets. A covalent bond, they actually share those electrons instead of, my fingers represent electrons. One electron coming from one atom, one electron coming from another atom, and they come together, entwine with each other, and literally share those two electrons. There's going to be equal sharing and unequal sharing, which is related to the electronegativity. But covalent bonds either will share those electrons equally or not equally. Okay. They're unlike the ionic bonds that are just electrostatically connected to each other. Here's the main difference. When an ionic bond is dissolved in water, they literally break apart into their ions again. Okay. And sodium chloride, if I take sodium chloride and I make salt water, I dump it in water, the sodium ion plus ion and the chloride ion dissociate and they break apart completely. Okay. Those guys will conduct electricity. Ionic compounds will conduct electricity because those are the ions. Those are the electrolytes that go into solution. Okay, that's why you need electrolytes in your body after you work out, because those electrolytes are what are conducting electricity and messages in your body. They're ions. Covalent bonds, and there's only one exception, but for right now, just say we'll talk about those when we get to it. But covalent bonds, when they are bonded together and we put them in water, they do not break apart. Okay, and therefore things like sugar, which is a covalent bond, when we put sugar in water, it will not conduct electricity, because the reason it won't conduct electricity, there are no ions. Okay. Pure water, 100% pure water will not conduct electricity. It is only that you put in a pinch of salt or a pinch of ions, like an ionic compound, that goes in solution and therefore conducts electricity. So I tell students, don't try this at home, but you could, let's say a lot of people, they tell you, don't put you're in the bathtub and don't fill it up with water and use your hair dryer while you're in the tub, right? They tell you that. Why? Because the hair dryer falls in, that water, that tap water is full of ions. It will conduct electricity. Now, if you were in a tub of pure 100% water, you throw in that electrical, don't do this at home. You put in the hair dryer in that water, it will not conduct electricity. Nothing will happen. There are no ions with you in there. But after a while, you need to get out of the tub, because on your surface, you have all kinds of ions that eventually will dissolve, and then it will start conducting electricity, and you want to get out of that tub real quick. All right. So, but don't do that at home with pure water. So covalent bonds made up of non-metals. So again, we go to the periodic table. We got to find out who's a metal, who's a non-metal. Combination: carbon dioxide, carbon and two oxygens, two non-metals. H2O, water, two non-metals. Okay. Nitrogen gas, N2, two non-metals. Those are covalent bonds. So here's some example: carbon dioxide, carbon monoxide, all the hydrocarbons that you use to burn your car fuel in your engine, all covalent bonds. Okay. Now, again, the main difference between these two chemical bonds, ionic bonds, and there is no sharing of electrons. It's an attraction between a full charge positive and a full negative charge that come together and are attracted to each other because of the charge. Covalent bonds, there's a literal sharing of electrons. That sharing can be equal sharing or unequal sharing. And we're gonna the subset of covalent bonds will be what we're gonna learn with time here. Covalent bonds will give you either polar bonds or non-polar bonds. Okay, but we'll get to that. All right. So now in writing bonds together, specifically ionic bonds, your brought here says, why is the formula CaBr subscript 2? Okay. Why is that? Well, here's the thing. Remember this. When we put ionic bonds together, we started first with the ions. Okay. We know that calcium, ionic calcium, is in group 2. Well, elemental calcium group 2, so is ionic, but it's in group 2, meaning there's 2 valence electrons. When it becomes ionic, it has a plus 2 charge, right? Okay. And that is true for everybody in group 2, all the metals in group 2A. Okay. When they become ionic, they all will have a plus 2 charge because they have 2 valence electrons. And by losing those 2 valence electrons, the next valence shell is now full. They have fulfilled the octet. The bromide, it's not Br2 thinking it's bromine. Remember, that's something important too. Notice the formula: Ca calcium and then Br subscript 2. Okay, if calcium was not there, then you could say that's bromine. But calcium is listed first and then followed by the nonmetals. So we're not talking about bromine. We're talking about 2 atoms of a bromide, which means it's ionic compound. So we need to go back and figure out, okay, what kind of charge does the bromide have? Well, it's in group 7 as bromine, as it becomes bromide because it picks up 1 electron. And by picking up 1 electron, and now has an octet. The new valence shell now is fulfilled because bromine has 7 valence electrons. It's got 1 room for 1 more. Okay. So those are the ions to begin with. And remember, when we put them together to make a formula, to write a formula, we have to put them together such that we have enough negatives to cancel out the positives. So in this scenario, we need 2 of the bromides. Each one has a negative 1. So we need 2 of them. And when we put them together, that coefficient 2 becomes the subscript, and hence the formula for calcium bromide. And that is the name. As well start learning the names here. Calcium bromide. No, I didn't say bromine, because remember, the nonmetals, when they become ions, we change the name to the IDE. So calcium bromide is the name for that formula, for this compound. Okay. All right. Now remember, in this scenario, bromine is not diatomic, because the general format when writing formulas is ionic compounds. What is written first, what you see first, is the metal, in this case calcium. Then it's followed by whatever is bonded or attracted, in this case, attracted to calcium, in this case, the bromides. And the subscript tells you how many of each. So you got 2 bromides for every calcium. Okay. All right. Now, the question asked here is, which compounds are ionic? Okay. And to answer this, you have to go back and refresh your memory as to what is defined as ionic. And you'll see from the previous couple of slides that is a compound that is ionic is the combination of metal and nonmetal. Okay. So let's go through this. We have the first one, which is K, which is potassium, and bromide. Would you think that is ionic? Who can tell me that would be ionic? Potassium and bromide.
Yes.
Yes, okay, because we got potassium is a metal, the bromide is a non-metal. So definitely KBr is ionic. All right. The next one has sulfur and oxygen. Notice that sulfur is written first, right? And then followed by whatever is bonded. So in this scenario, you'll find you will learn that the first atom is generally the central atom. And then these three oxygens are bonded around the central atom. Okay. But sulfur is a nonmetal and oxygen is a nonmetal. So that is not ionic. That would be a covalent compound. Okay. That, by the way, is called sulfur trioxide. Three oxygens meaning trioxide. And very nasty smelling gas. In fact, if you ever get in the vehicle, you're behind a vehicle and you smell this kind of a smell of a rotten egg smell, and that's what you're smelling from the vehicle, giving off some sulfur trioxide. That eventually goes up in the atmosphere, reacts with water, and eventually makes sulfuric acid, which is an acid, and then comes back down in the ground and causes all kinds of other problems. All right, the next one, we got hydrogen and the chloride. Notice I didn't say chlorine because it's bonded to something. This is hydrogen and chloride. This is, again, not ionic because hydrogen is not ionic, even though it's in group one. Remember I said it's in group one, doesn't mean it's to the left of the star step, but you'll see it in periodic tables, it's kind of different color. It's a non-metal. This is what's roaming in your stomach right now. Hydrochloric acid, that is the formula for hydrochloric acid. Very acidic. Okay. The next one, the fourth one, we got Br2. Now, unlike what we saw earlier with the calcium was written first, all we see here is Br2. That's an indication we're dealing with the diatomic element, okay? Bromine. Again, there's two bromines, okay? Two bromines meaning they are not ionic because they're non-metals. And then the next one, we have carbon and oxygen. Again, carbon is written first, so 9 times out of 10, that's the central atom, and then you have oxygen around it. That is called carbon dioxide. We all heard of that one too. Again, two nonmetals, therefore not ionic. And then finally, we have magnesium chloride. Magnesium chloride. Where previously we had the calcium, now we got magnesium example. So we got a metal and a non-metal. Okay. Metal and non-metal. So of these listing, those are the only ones that are ionic compounds. The other 4 are covalent compounds. Covalent compounds. So SO3 is sulfur trioxide, HCl is hydrochloric acid, Br2 is simply bromine, and CO2 is carbon dioxide. Okay. All of them covalent. These are the ones I've highlighted in yellow are covalent, the others are ionic. All right, so now with respect to ionic compounds and ionic bondings, electrons are totally transferred from one element to the other. In this scenario, you have chlorine atom and sodium atom combining together to form what we put on our French fries, sodium chloride. Sodium, remember, has one valence electron. It's a metal. It's going to lose electrons. The chlorine atom is in group 7, okay? It's in group 7. It has room for 1 electron. And so by sodium giving up that 1 electron and giving it to the chlorine now has 8 valence electrons around its shell. Remember, it has 7 valence electrons. It belongs in group 7A. There's 7 valence electrons. And so it's this halogen, remember the special name halogen? These halogens want to pick up 1 electron to fulfill that magical 8. Okay. Sodium, on the other hand, by giving up that 1 electron, now the next layer, the next energy level is the next one in. It's full. It's now has an octet as a sodium ion. Also, take a look at the relative size, the diameter of the color. You see sodium ion compared to the sodium atom compared to the sodium ion. The ion is much smaller. Okay. Again, because it lost that 1 electron. And then the chlorine atom in green is much smaller than the chloride ion because the chlorine atom picked up an electron, take up more space so that its particular radius decreases. So that really demonstrates here what happens to the cation and the anion with respect to radius when you compare it back to the atom itself. And so in essence, as a general trend, you can see metals on becoming cations decrease in diameter. Non-metals on becoming anions increase their diameter or radius, if you will. Radius or diameter, same thing. Okay. So do notice that site changes. And then in solid crystalline state, you can see how it's very ordered as far as the sodium ion and the chloride ion combined together. Now, what happens is these sodium chloride, here's the crystal structure of it, okay, very structured, very ordered. When it goes into water, all that breaks apart. And that is what causes or allows it to conduct electricity because these ions are now in solution, and they can give you a charge. All right, now, this is a rehash of what we talked about before. We got magnesium atom, has 12 protons and 12 electrons, okay? It is in group 2A. When it becomes the ion, now that reminds me, I have a few questions concerning the electron configuration of atoms versus the ions. So keep in mind here that here we got the atom and here we got the ion. The +2 means it lost 2 electrons. So it has a different electron configuration than the magnesium atom. The magnesium atom will have on the outside the 3s2, whereas the magnesium ion will not have the 3s2 because it lost those 2 electrons. Okay, so keep that in mind when you write electron configurations for the atoms versus the ions. So as they became the ion, magnesium 2 lost 2 electrons, okay? Sulfur, again, has 16 protons, 16 electrons. It is a nonmetal, okay? It's in group 6. It needs 2 electrons to make the happy 8, okay? The octet rule. So it will pick up 2 electrons. And now it has a total of 18 electrons, giving it a full -2 charge. So these 2 ions will come together because we've got the +2 of magnesium and the -2 of the sulfide. Notice the name change, sulfur to sulfide, okay? And they come together by what are called electrostatic forces. So ionic compounds come together because of electrostatic forces, the positive charge and the negative charge. Totally different from the covalent compounds where there are no charges involved. Okay. At this time, we're going to be talking about partial charges later on, but not a full charge like we find with ionic compounds. Okay, so this is just a recap about the ionic size. You know, I just mentioned cations, they lost electrons, and so they're going to be much smaller because they lost electrons. And the anions are going to be much greater because they picked up electrons with respect to their respective ionic size of the ions. Okay. So, true or false regarding an ionic bond between aluminum and iodine? Okay. Aluminum atom loses electrons and the iodine atom gains electrons. Would you guys say that's true or false?
True.
That's correct. Okay. Because aluminum is a metal, the iodine is a nonmetal. Okay. And so the nonmetal will gain electrons, whereas the metal will lose electrons. Now, the aluminum ion is larger in radius than the aluminum ion. Is that a true statement? Think about what aluminum, when it becomes an ion, what did it do? It lost. It's a metal. It's going to lose electrons. And specifically, it's going to lose 3 of them. Okay.
So the aluminum atom is larger.
That is correct. Okay, let's go back to this. Notice the, let me draw my arrow here. When we compare the relative radius, and that circle represents the relative radius, okay? On the far left of the arrow, this is the arrow telling us a process occurred. So that's the reaction arrow. So the red arrows, I'm pointing to the sodium atom. It is an atom, it's going to lose electrons, and look what happens to its radius, okay? We can see here that when we compare the radius here versus here, the radius of the atom greatly decreased. Again, because the sodium atom is a metal and it lost that 1 valence electron. It's in group 1. And so sodium, if you look at the period, sodium atom is in period 3. So it's got 3s1 electron out, the 3rd energy level. When it loses that electron, well, that energy level is empty. So the next one is the 2nd energy level. And that's full. Okay, so now the diameter is much smaller. Now the chlorine atom has an X diameter now, but it's in group 7. There's 7 valence electrons. It's going to pick up 1 electron. And when that happens, it picked up 1 electron, so its diameter gets bigger. So the nonmetal gets bigger by picking up an electron, okay? So with that in mind, when they ask you these questions, you know, that's a true statement, and that is a true statement. The aluminum atom, which is in group 3A, will lose 3 electrons. Okay, which is in 3, its valence shell is in the 3rd energy level. By losing those 3 electrons, now it now has the 2nd energy level, which is full. Okay. The iodine atom is smaller in radius than the iodine ion. Again, that is a true statement, just like we just talked about with the chlorine. Okay. And then finally, the aluminum ion and the iodide ion form a bond by attraction. And that is a true statement because the aluminum ion is now a +3 and the iodide is a -1. There's 3 of them and they come together by electrostatic attraction. Okay. Now, as far as metallic bonding, we're not going to say much about them other than to say that pure metals are just a sea of electrons. That's why metals are very good conductors. They have a lot of electrons on the surface, and they can conduct electricity very well. And because they're good conductors of electricity, they also are good conductors of heat. And that's about as much as we're going to say about metals. Okay. Now, with respect to covalent bonds, so we talked about electrostatic or ionic bonds, which are electrostatic attraction, like two magnets coming together. Now, we're going to talk about covalent bonds. In this example, the bonds are shared, okay, are shared. So electrostatic, here I represent with my two hands just coming together. Covalent bonds, I represent those by my fingers interlocking with each other, interlacing with each other, where I'm forming a literal bond. Now, there's three types of bonds in the covalent bond. There's a single bond, a double bond, and a triple bond. Okay. Now, and what you're going to see is a simple line. Okay. And so a single bond could be denoted by a single line like I'm writing here. A double bond can be written by two lines, exactly like I got here. Okay. And then a triple bond, guess what? Three lines. I'm going to draw them a little bit off a little bit. So three lines. Okay. Now, each line represents two electrons. So in the single bond, there are two electrons. Let me get my arrow here. So there's two electrons in that single bond. Okay. A double bond, there are four electrons. This represents the double bond. Each line represents two electrons. And obviously I didn't draw it very well, but there's three bonds together there. Okay. And there are six electrons. And so you'll find that, for example, if I were to draw a double bond or write them out, I could say carbon, and I can use my equal sign in carbon. That will represent a double bond, if you can see that. Okay. If I were to do a single bond with carbon, then it would be carbon, say hyphen, let's make that capital C, hyphen capital C. That is a single bond. Okay, double. And I'm going to see if I can draw. A triple bond. It's going to be tough, but I'll draw it right here. Okay. Hope you can get the gist of it. That's a triple bond. Okay. And so every line, let me see if we can draw it again. There we go. That's a little better. Okay, single bond, double bond, and a triple bond. Okay. And there's some examples here that you carbon dioxide covalent bond. Again, what's in a covalent bond? That's a combination of two nonmetals. So we got carbon and oxygen. Okay. The black sphere represents the carbon, and the two red on each side represent the oxygen. If we look at that's a space field model. Okay. If you look at H2O and a space field model, the oxygen is a central atom, and the two hydrogens there are the bonded. Now, as I stated earlier, normally 99% of the time, the first atom written is the central atom, as the case with carbon dioxide. Okay. But by convention, water is written with H2O first. And it's one exception where the hydrogens are not the central atom, but oxygen is. Okay. It's only one exception. There are a few others, but by and large, the majority of the time when you see the first atom written like carbon dioxide, that is a central atom, and that everything else is bonded around it. Okay. All right. So here's some of this out here. Now, single bonds, 2 electrons, 1 pair, they're being shared. Okay, double bonds, as I mentioned earlier, 4 electrons for 2 pair, they're being shared. And 6 electrons for a triple, meaning there's 3 pairs, and those are being shared. Okay, they're sharing bonds. Now, with respect to strength, single bonds are generally the longest as far as measuring the distance between the 2 atoms that share a single bond. They tend to be the weakest within the single, double, triple bond category. And triple bonds are the shortest with the distance between the 2 atoms, for example, and they tend to be the strongest. Being the strongest, they also have the highest amount of energy. And for example, acetylene, if you're not familiar with acetylene, it is a gas along with oxygen used to burn steel. Okay, so you have acetylene torch. A lot amount of energy there, strong enough heat to burn steel. But things like butane, we're all familiar with butane. You flip your Bic, they're just single bonds. And propane, those are all single bonds, and they got energy in them, but not enough to burn steel. Okay, enough to cook your hamburgers and light your cigarette, but not to burn steel. But triple bonds are the shortest and have the strongest. Now, it was thought then with respect to covalent bonds, and remember, with ionic bonds, when they come together, there's electrostatic attraction. So there is a radius between the nucleus of one atom and the other. Okay, there's no sharing going on. With covalent bonds, there is sharing going on. All right, so it was thought, for example, if we look at the hydrogen atom and the chlorine atom, when they got together to form the hydrochloric molecule, HCl, it was thought that the bond angle of the two would be the sum of the two, but that's not the case. It turns out that the bond length between the chlorine and hydrogen is much less than the combined. Hold on, we've got time. Oh, yes. All right, let me finish this slide and I'll be done with it. Very quickly, let me just highlight it. Thank you for the reminder. I get a little carried away sometimes. If we look, this is the bond angle. NM is just nanometers, just units of length. Not to worry about them, but you can see each one has their own individual radius, okay? Now, it was thought that if the radius of hydrogen and chlorine were to combine, that would be the radius of 0.136. Turns out that's not the case. That the bond length between the HCl is literally smaller than the sum, okay, of the two. It's 0.127 versus 0.136. And that is because there is overlap in here. And that is where they are sharing those electrons. Okay, so they're not come up against each other like the ionic compound, but there's overlap. Okay, so all right. So with that being said, let me stop it here. We are on slide number 7, and that will be number 13, slide 13, chapter 7. Let me stop.